Suggestion is take the derivative. Integral. Yes, you're absolutely right. Integral. So let me go ahead. I need a little bit more room, so I'm going to close this for right now. We're going to integrate from, see, in radians, 30 degrees is what, pi over 6. 60 degrees is, and that's a minus pi over 6 to pi over 3 of our omega d omega. And you're probably shaking your head and saying, what do you mean I got to integrate again? Whoops, sorry. I'm putting my limits of integration at the wrong spot. We're integrating from omega naught. Let's just go ahead and put in there 0. We start from rest to some omega. Omega d omega equals, yes, we're using our calculus again, minus pi over 6 to pi over 3 of this expression, m divided by I-O minus k I-O cosine theta d theta. Okay? Slide on over here. So how much more room do we have to work with? We can integrate that. So we got 1/2 omega squared equal to our m over I-O, again the value, times theta. What's the integral of cosine? Negative sign or positive sign?
Negative sign.
Negative sign. Thank you. So that means we have negative, negative, so we would put a positive. K over I-O sine theta. Evaluate it from where? Again, from a minus pi over 6 to pi over 3. Everybody agree? So we took the integral of cosine should be
I think you
minus sign. Go ahead.
I think you keep minus sign theta. I think.
The derivative of sine is cosine.
Mm-hmm.
So the integral of cosine is sine. So we should keep that minus sign in there.
Exactly.
Okay. Thank you. Yeah, but if derivative of sine is cosine, then the integral of cosine is sine. Thank you very much. So we have here what omega is when we launch. Omega at 60 degrees. Some radians per second is what you're getting. Okay? So I'm going to resketch. Now that we know that, resketch my arm here. We've got our ball. We're launching at the velocity of b. We're at our 60 degrees. Again, we know this omega at this point. So let's go ahead and call it omega 60. Let's do that. This is our omega at 60 degrees. What's the velocity of the ball when it launches? Well, we know velocity of the ball is going to be the radius to the ball times that omega at 60. Okay? So you can figure that part out. And of course, your radius, let's go ahead and identify that again. This is our 22 1/4. Is our distance there. what will be helpful to go ahead and identify in this diagram is if we're 60 degrees there, 60 degrees look like we're launching at 30 degrees, would be our angle that we're launching at. So the question is, why do we take the integral of omega from 0 to omega? I wanted to know what the angular velocity is at my angle that I launch. So I could, I set up my limits for the angular displacement to where it started, the minus 30 degrees, which up, I think we're good to go there, to the 60 degrees. So what is we started from rest. As soon as the, launch action started to happen, we started rotating that swing arm. Initially, the ball and the arm were not moving in the angular direction at all. We had no angular velocity. But the instant we apply that moment, we now have that, very short time frame that it's rotating the swing arm and launching the ball. So again, we know that range of motion, and we can figure out the angular velocity at the time that the ball launches from the cup. So with that, we know our velocity, know the angle of launch. How do we figure out the range? So you're going to have to help me out here to figure out the range for a projectile. This is where you've got your, see if we can go ahead and set up our equations. We know, see, we got a y equal to y naught plus our vy naught t plus 1/2 g t squared. And for that matter, it should actually be a negative since it's a negative g. So 1/2 your negative g is your acceleration, t squared. So basically you're going to go from 0 to 0. So you can figure out a time increment. So that means your x equal x naught plus your vx naught t. You don't have any acceleration in the x direction. So you can figure out your time interval to solving that quadratic equations. You got two possibilities of time. Pick the one that you can go from 0 to 0. I know, you could, if you want to figure out, well, okay, what's the time it takes to get to the apex of the projectile curve, double that to figure out the full range. But basically solve for your time. And your range is going to be your x. Figure that part out.
So you're saying it's the time to go from 0 to 0, but if you're starting at the apex, or if you're starting at 60 degrees, then it's above the table. Ah. So do we need to account for that?
Yes, you should be able to account for that.
Okay.
So if you're going to use your horizontal plane as your indicator, I said I didn't give you the overall height of the FlingerBot, so we won't worry about taking that into account. But you're absolutely right that if our horizontal plane at the pivot point is our 0 point, then our y naught would be whatever that height is, your sine of your 22¼ times the sine of 60 degrees. So that's where you start off at, and you end up with you end up at 0 for the full range. So thank you. That'd be a better way to estimate the range.
So we're trying to find the position where the ball comes back down to the pivot point, or equals the pivot
point.
point?
To the pivot point.
Okay.
So we could make the assumption, if we look at our demonstration video, we could make the assumption that the hoop's at the same level as the pivot point. Because that's, of course, what I'm driving forward is that one of these days I'm going to get this project set up so that we can do the calculations and we can know exactly how much to, what distance to set it at and how much force to apply and make our 3 points instead of having an air ball.